so this is our honors chemistry lesson video for section 13.4, and so in section 1, 2, and 3 we focused on gases, liquids, and solids. And so now we're going to focus on phase changes, or changes in state of matter. So the change of a substance from a solid to a vapor without passing through the liquid state is called sublimation. So this is what dry ice goes through. It sublimes. It goes directly from solid to gas. That's why it's called dry ice, because there's no liquid phase. Dry ice and iodine are two examples of solids that sublime. The state of a substance depends largely on the balance between the kinetic energies of the particles and the inner particle energies of attraction. So in other words, it's all about the kinetic energy of movement versus the intermolecular forces, which try to hold them together. So intermolecular forces try to keep particles together. Kinetic energy tries to spread them out. The kinetic energy, which depends on the temperature, tends to keep the particles moving. The inner particle attractions, or intermolecular forces, tend to draw the particles together. So you can look here, this shows that from solid to liquid to gas, we're increasing kinetic energy, which increases particle motion, but there's a decrease in intermolecular forces. Intermolecular forces actually increase going towards the solid. So these are our phase changes. Of course, from liquid to gas, they have called it evaporation, but that would also include boiling. So really the term we tend to use is vaporization. From gas to liquid is condensation. From liquid to solid is solidification or freezing. From solid to liquid is melting. From solid directly to gas is sublimation, like dry ice. And from gas directly to solid is called deposition. So really the only two you may not be familiar with before now are sublimation and deposition. So when we're talking about phase changes, we need to discuss the phase diagram. So a phase diagram is the relationship among the solid, liquid, and gaseous states of a substance, and it can be represented as a single graph called the phase diagram. And so it shows what state of matter a substance will be at any temperature and pressure. The lines on a phase diagram indicate the conditions at which two phases occur in equilibrium, or it means there's a phase change that's happening. The triple point describes the only set of conditions in which all three phases occur in equilibrium. So this is an example of a phase diagram, and this one happens to be for water. So if you look, we have temperature across the x-axis, we have pressure in ATM up the y-axis, and then you can see that you have these lines, and it kind of makes this Y shape. So this area, all of these temperatures and pressures, is when water will be in its solid form, will be in ice. Okay, so if you look at normal pressure, 1 ATM, we have solid, 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 all the way until you hit 0 degrees. Because what happens at 0 degrees, it melts. So that's what MP stands for. This would be the melting point. Now notice, melting point doesn't change much. Now this line isn't perfectly straight up and down, but it's close. So melting point doesn't change much with pressure. Now, so when you're on the line, that means it's in the process of melting. So you have solid and liquid together. So we say those are in equilibrium. Once all of it melts, then we can start increasing our temperature again, and we become a liquid. So at all of these temperatures and pressures, we're in the liquid phase. So if we keep heating it, keep heating it, keep heating it, eventually we hit 100 degrees Celsius. And so now we've hit another line, and this one's between the liquid and the gas, which means now we are about to boil. So this is called NBP because it means normal boiling point, because it's at our normal atmospheric pressure, 1 atm. Notice, on the other hand, how much boiling point changes with temperature. All right, so that's why it's called the normal boiling point. And so on this line, the liquid and gas exist in equilibrium. You have some liquid and some gas while it's boiling. And then eventually, once it all boils, it becomes a gas. And so that's what's going on. Now, it is also important to note that the slope of this line, like the line is pointing slightly in this direction, because we'll talk about that in just a minute. But the next thing we're going to talk about is what this point is right here, like what's happening up here. And so what I want you to notice is it's called C on here. It's called the critical point in real life. What I want you to notice is the two states of matter, liquid and gas, their colors just kind of start merging. So let's talk about what's happening there. So the critical temperature and pressure, which is happening at the critical point. The highest temperature at which a distinct liquid phase can form is referred to as the critical temperature. The critical pressure is the pressure required to bring about liquefaction at the critical temperature. So once you get past the critical point, it's hard to distinguish between the liquid phase and the gas phase. Because remember, although we like to make two distinct separations between the two, there is an area where they just kind of become one and the same. All right, so that's what's going on at your critical point. So above the critical temperature, the kinetic energy of the molecules is greater than the attractive forces that lead to the liquid state, regardless of how much the substance is compressed. So in other words, we reached a point where they have so much kinetic energy, no matter how much we increase the pressure, we can't get those particles to liquefy again. The greater the intermolecular forces, the greater the critical temperature, because more intermolecular forces mean the particles want to be together. So you would have to heat it even higher to get enough kinetic energy to where they would not come back together. All right, and past our critical point, it's just called a supercritical fluid. So now let's talk about that slope of that line. So on the phase diagram, it's important to note that here is a straight or a perfectly vertical line. And so you can see the solid-liquid equilibrium line has a slope back towards our y-axis, or like a negative slope. Whereas most substances, if you look, here's my vertical line, most substances, theirs has a positive slope. It slopes away from the y-axis. So what is happening there? Like, why does that happen, and does that make a difference? So the solid-liquid equilibrium line for CO2 slants to the right with increasing pressure, telling you that the melting point increases with increasing pressure. So I'm going to click back real quick. So I can see that as my pressure increases, my melting point is increasing. Now again, it's not a large increase, but it is a small increase. However, the solid-liquid equilibrium line for H2O slants to the left with increasing pressure, telling you that melting point actually decreases with increasing pressure. This atypical behavior is due to the fact that liquid water is less dense than ice. So if we look back at water, so that's one of the ways where if they just gave you a phase diagram and had you identify the substance, if it's water, you'll notice that solid-liquid equilibrium line slanting to the left. Most substances, it slants to the right. So what this is saying is that as pressure increases, my melting point actually decreases, which means that the liquid state is more dense than the solid state, which is, of course, why ice floats on water. So let's look at some questions that you could be asked about a phase diagram. I mean, I only wish that you would get something this easy, because this one's super easy. So referring to the phase diagram of water, describe any changes in the phases present when water is kept at 0 degrees Celsius while the pressure is increased from that of 0.1 to that of 0.5. So we're down here and we're going from 1 to 5. So let's write what's happening. So at 1, we're at a gas. And then eventually we switch over here to the solid phase. And then we keep going up to 5, and then we hit the liquid phase. Okay, so it says describe any changes. So in other words, first it goes from gas to solid, which is of course deposition. And then it goes from solid to liquid, which of course is melting. So those are the two things that are happening. So first I listed just the state of matter changes, gas, solid, liquid. And then I listed what those were called. So from gas to solid, it's deposition. And from solid to liquid, of course, it is melting. So see, that was super easy. Now, of course, the phase diagram might not tell you solid, liquid, or gas. So make sure you know where those are located. So we have gas to solid to liquid, and that's called deposition and melting. So part B, it says if it's kept at 1 atm while the temperature is increased from 6 to 9. Okay, so now we're looking across. So first I'm just going to write my states of matter. So I'm starting with the solid at 6. And then eventually I hit the liquid phase. And then of course I get to the gas phase. So what state of matter changes are happening? Well, solid to liquid is melting. And liquid to gas is boiling or vaporization. Either one's fine to write. Alright, Alright, so hopefully you found those pretty easy. So solid, liquid to gas, melting, and boiling. So maybe try this one on your own, then we'll look at it together. So it says, using the phase diagram for CO2, describe what happens when the following changes are made to a CO2 sample. Pressure increases from 1 atm to 60 atm at a constant temperature of negative 60 degrees Celsius. Alright, so I'll assume you paused it and tried it. Okay, so they don't have negative 60 labeled on here for me, but I can see that this is negative 78, and I can see the triple point is at negative 57. So I know I'm somewhere here at negative 60. Okay, so we're not on the triple point or to the right of the triple point. We're somewhere to the left of the triple point. All right, so it says we're increasing from a pressure of 1, so we're about right here, atm, to 60 atm. Again, it doesn't tell me where that is, but I can clearly see I'm increasing temperature a lot. So it says, what happens when the following changes are made? Well, we are clearly going from a gas, you can see I'm in the yellow area, to a solid. So what is directly from gas to solid? It is deposition. So hopefully you got that one right. I like phase diagram questions. I just like phase diagrams in general. Like, it's just kind of cool. All right, so hopefully you got that one right. And then maybe pause it and try this one. Okay, so I'll assume you've done that. We'll look at it together. So it says temperature increases from negative 60 to negative 20. So again, I can't see exactly where negative 60 is, but I can assume it's here. This says 31. So and then it tells me critical points at 31. So I'll just assume that negative 20 is maybe about right here. Sorry, we're not at negative, oh yeah, we are, negative 20. So we have negative 60, so maybe negative 20 is about right here. At constant pressure of 60 atm. So again, here's 1, so I'll just assume 60 is way up here. So we're starting at negative 60, and we're going to negative 20. So I'm going from here to here. So what's happening? Well, we're going from solid to liquid. So that means we are melting the substance. Melting the substance, solid to liquid. And see, notice this is carbon dioxide. And so I know we talked about how it's dry ice, so you might think, well, how is it a liquid? Well, it goes through sublimation if you're at normal atmospheric pressure. See, it goes directly from solid to gas. If you increase the pressure, though, you can force it to become a liquid. It just means at normal atmospheric pressure, it skips the liquid phase. All right, so hopefully you're finding phase diagrams pretty easy. So it says, what does the triple point on a phase diagram represent? It represents when all the states of matter exist in equilibrium. So if you look, the triple point right here, see how all the states of matter touch it? That means at the triple point, at this specific temperature and pressure, you will have some solid, some liquid, and some gas, all in equilibrium. So triple point shows the temperature and pressure in which all 3 states of matter exist in equilibrium. All right, so let's knock out our sample integrative exercise. This one's kind of long. This will get you ready for what it'll be like to have a never-ending free response question on the AP exam, except this one's way too easy to be on that. So it says the substance CS2 has a melting point of negative 110.8 and a boiling point of 46.3 degrees Celsius. Its density at 20 degrees Celsius is 1.26 grams per centimeter cubed, and it is highly flammable. What is the name of this compound? Remember, when it comes to naming, you have to look at the first element. Is it a regular metal, a transition metal, or other element with multiple charges? Is it a nonmetal or hydrogen? It is a nonmetal. That means I'm going to use prefixes in my naming. So C is carbon. I don't use a prefix if the first element only has 1, so I'm not going to call it monocarbon. And sulfur becomes sulfide. Remember, we add I to the second element. And it has a subscript of 2, so I need the prefix di. So it would be carbon disulfide. Carbon disulfide. Part B, it says list the intermolecular forces that CS2 molecules would have with each other. Well, if you subtract your electronegativities, which I'm not going to do this right now, if you have your electronegativity chart, if you subtract them, they are very close in electronegativity. So of course they are going to have London dispersion, of course, because all molecules experience London dispersion. But they would possibly have super, super weak dipole attractions just because they aren't the same element, although when you subtract, those two are so close together. But if you draw the Lewis dot structure, you end up with this right here. And so if we did try to put the dipoles on there, they will cancel out. So even if you forgot to subtract, or when you subtracted you didn't realize it was practically nonpolar, and you thought there might be dipole attractions, super weak ones hopefully, you can see that they cancel. So there would be no dipole, it would just be London dispersion here. All right, so let's look at our other parts. All right, so it says, predict what type of crystalline solid CS2 would form. Well, is it going to be ionic or molecular? Well, it's two nonmetals, and it had a super low melting point, so it would be a molecular solid. Ionic tends to have a higher melting point, and is usually a metal and a nonmetal. Part D says, write the balanced equation for the combustion of this compound in air to produce carbon dioxide and sulfur dioxide. So I start with my CS2. Remember, combustion is when something burns in the presence of oxygen. So even though it says air, we know it's going to react with the oxygen, which is O2. And then it tells me the products, carbon dioxide, CO2, and sulfur dioxide, SO2. And then we got to balance it because it says write the balanced equation. So I have 1C, 2 S's, and 1 S, so I put a 2 here. 2 oxygens, and then here I have 2 and 4, which is 6. So 3 times 2 gives me 6. Alright, so hopefully these have been so easy pretty far. I mean, been pretty easy so far. So easy pretty far. Alright, so let's move on to the last part. So it says the critical temperature and pressure for CS2 are 552 Kelvin and 78 atm respectively. Compare these values with those for CO2, which is only 304 Kelvin and 73 atm, and discuss possible origins of the differences. Well, I can see that CO2 has a lower critical temperature and pressure, which implies that since CS2 has a higher critical temperature and pressure, it has higher intermolecular forces. Well, both of these are nonpolar and only experience London dispersion. So what could be the difference? Well, remember, London dispersion forces increase as molar mass increases. If I add up CO2 off the periodic table, carbon is 12 and oxygen is 16 times 2, I get 44 grams per mole. If I add up CS2, carbon's 12 and sulfur is 32 times 2, I get 76 grams per mole. So CS2 has the higher critical temperature and pressure due to the fact that it has more London dispersion forces since it has a higher molar mass. So here, I'll click that so that you can copy that down if you want to. So the values for CS2 are larger because CS2 has more London dispersion forces due to its higher mass. And then the last one, would you expect the density of CS2 at 40 degrees Celsius to be greater or less than at 20 degrees Celsius? What accounts for this difference? Well, most substances, as you increase the temperature, density decreases, and that's because as you heat the particles, they want to spread out more, increasing the volume. If you increase the volume but the mass stays the same, density decreases. So the density would be lower at 40 degrees Celsius because the particles spread out and take up more volume. Alright, so hopefully you didn't find phase diagrams too confusing, and the main thing is just make sure you remember sublimation and deposition because those are the most common phase changes that people forget, and then just make sure you understand how to work your way around a phase diagram.